All right, welcome everyone. Happy March. Happy daylight savings to those who celebrate. So our presenter today is Lizeth Magaña, who is all the way at the end of the other end of the hallway from me at APL. And Lizeth will be talking to us today about some very exciting UV observations that she did as part of her dissertation work. So I will just remind everybody, if you're not speaking, to have your microphones muted. So Lizeth, one question for you. Would you prefer, so if folks have questions, would you prefer if we hold them until the end, or would you prefer if we sort of spoke up in between? Either of them is fine. But
yeah, I think if it's a small question that clarification, or maybe just any question, just better just to interrupt me.
All right, so small questions we'll interrupt, larger questions we will hold until the end. And Michael and Rick want me to point out that it's also Pi Day. So yeah, so it is the 14th of March. And about half an hour ago, it was, well, no, okay, I'm not gonna try going to more significant digits. But yeah, in fact, yeah, I guess shortly after this call, it will be 1529 on 3/14th. But yes, very important. But I will hand it over to Lizeth. And so Lizeth, I'll let you introduce yourself a little bit more, and I will go ahead and put myself on mute.
Sure, thank you, Parvati. So as Parvati mentioned, my name is Lizeth Magaña. I'm currently a postdoc at APL, so I've been here for all of a month and a half-ish. But the work that I am presenting here today, I did as a graduate research assistant at the Southwest Research Institute. And then at the time, I was a grad student at the University of Texas at San Antonio. So at the time, I was working with the LRO-LAMP team as well as Kurt Rutherford. So all of this work is really going to focus around the LAMP instrument. And we're going to be looking at condensed volatiles, both at the lunar South Pole and within the coma of one very specific comet, which was Comet Siding Spring. So to get started here, as I mentioned, we're going to be looking at water ice at the lunar South Pole. We're then going to take a step back. We're going to look at possible other volatiles at the South Pole, including NH3, SO2, and CO2. And we're also going to look at the coma of Comet Siding Spring and analyze some of the water production rates. So as most of us know here, there are a variety of mechanisms by which volatiles can enter the lunar environment. This includes comet and asteroid impacts, outgassing from the lunar interior, and also the creation of water through the interaction of hydrogen atoms in the solar wind and the lunar surface. So regardless of the mechanism that these volatiles are brought into the lunar environment, what we think happens is that these volatiles sort of hop along the lunar surface until they're either lost due to photodissociation, or until they reach one of the poles, either the North Pole or the South Pole, where they may encounter a permanently shaded region. So as the name indicates, these regions do not receive much, if any, direct solar illumination, which allows them to remain at extremely low temperatures. And what I mean by extremely low temperatures, I mean temperatures that, if water ice were present, it would be thermodynamically stable over the lifetime of 1 billion years. So these are regions that are less than 110 Kelvin. And so that's what I'm showing here on the left-hand side. So these are the 6 regions of interest, the 6 cold traps within permanently shadowed regions that we're going to be looking at. These include Cabeus, also Haworth, Shoemaker, Faustini, an unnamed region just to the right of Haworth, and then also the PSR within Amundsen. So as I mentioned, we're looking at the permanently shaded region. So we can't really use the sunlight as our illumination source. So with the Lyman Alpha Mapping Project, or LAMP, this is the UV spectrograph on board LRO. So as LRO orbits the moon, LAMP has this special capability of being able to use the background starlight and then also the Lyman alpha interplanetary medium as an illumination source within these PSRs. And so by doing so, we're able to look within these PSRs. And so this sort of thing has been done previously with the LAMP instrument by both Gladstone et al. In 2012 and also Hain et al. In 2015. But similar studies have also been done by other instruments on board LRO, including Lola, Diviner, and then also the M-Cubed instrument on board the Chandrayaan-1 spacecraft. So on the image here, what we're showing is the North Pole on the left, the South Pole on the right, and all of these green pixels are regions that are consistent with the presence of water ice. So the grayscale here is the annual maximum temperature, and we see that these green pixels are really concentrated within these extremely cold regions at both poles. Now, with some of these previous studies, there was also a modeling component. So with the LAMP instrument, the spectral mixing models showed that there may be as much as 2% water ice by mass within these regions. But the study by M-Cubed found that there may be as much as 30% water ice by mass within very isolated regions. There was also the LCROSS instrument. So this was when we sent an impactor into the PSR in Cabeus crater, and we measured the plume that resulted from that. And so by doing so, we detected water, but in addition to that, we also saw NH3, SO2, and CO2 being the primary volatiles besides water. So in this study,
hey, Lizeth, just to interrupt you real quick, is it possible there's something hitting against your mic? So there's like a tiny bit of background noise, if not an issue, but you know, just FYI. But we can hear you fine, but just in case there's something next to your mic, we might be picking up that.
I'm not really sure because I'm using my laptop as my mic, so I don't really have a mic.
Okay, yeah, no worries. Not a big deal.
Yeah. Well, hopefully that works for everyone. Let me know if I need to change my audio source. So in this work, we're going to be building off of all these previous studies. So to do this, we're going to focus on those 6 cold traps that I mentioned earlier, but we're also going to include all observations, that is each individual orbit strip between 2009, which was the start of the mission, and 2016. So we're going to incorporate about 5 years of data, more than any of the previous LAMP studies. We're also going to use new waveband definitions, which I'll get into in a few slides here. And we're implementing a new data filtering process, which I'm not going to talk about today, but it is included in the paper if you are interested. So with LAMP, we are able to define our own wavebands. That is, we're able to look at any wavelength region that we choose within our passband. So we choose 3 different wavebands. These are the on-band, the edge band, and the off band, and they are defined specifically based on the spectral shape of water in the far UV. So if we look at the image in the bottom right corner, the on band is between 148 and 162 nanometers. And so we can see this is where water ice is not very reflected in the far UV. The off band is sort of the opposite. This is where water ice is very reflective. And then we have the transitionary region, which we call the edge band. So this is within 164 and 173. So since these waveband definitions are defined the way that they are, we can see that a high off-band to on-band ratio can then be used as an indication for the presence of water ice. So on the left-hand side here, I'm showing South Pole maps in the on-band, the edge band, the off-band, and then the off to on-band ratio in panel D. Now from panel D here, the off to on-band ratio, we can also look at the average off to on-band ratios within each one of the regions of interest. And that's what I have plotted here in the map on the right. But it is also the blue diamonds if we look at the plot on the left. As I mentioned, our waveband definitions we define specifically on the spectral shape of water. But the previous studies did a similar thing, but they actually used much wider waveband definition. So whereas our on band was 148 to 162, previous studies used 130 to 155. Same thing with the off band. The previous studies used an off band between 155 and 190. So to allow for a proper comparison, we went back to this waveband definition, found the off to on band ratio, and that's what we have plotted by the purple crosses here. So comparing our off to on band ratios with those from previous studies, we find pretty good agreement within 25% for one waveband definition and within 40% for the other. Now, the other really cool thing that we can do with LAMP is we're able to look at the spectra for any region on the map. So what I'm showing on the right-hand side is the spectra for the cold traps in blue, and then the spectra for the surrounding non-cold trap regions in black. So the top panel is the average of our 6 regions of interest, and the bottom is the average of all cold traps at the South Pole, period. So by looking at these two and comparing by eye, we can see that our 6 regions of interest that we decided on are a pretty good representation of all the cold traps at the lunar South Pole. The other thing that we notice is that the blue curve, the cold traps, are uniformly lower than the non-cold trap spectra, and this is true at all wavelengths. So the blue curve is actually about 13% lower than the surrounding non-cold trap spectra. And this is consistent with increased regolith porosity within these permanently shaded regions. This was shown by Gladstone et al. In 2012, but also in the spectral mixture models that we conduct that I'll talk about further on. We're able to show that the increased regolith porosity can completely account for this shift in y-axis here. The other thing we notice then is at the off band, we have this increasing albedo. Again, this is true within the cold trap spectra and also in the surrounding regions. So for the cold trap regions, this increase in off-band albedo could be due to condensed H2O. The interesting thing is that we see it in the surrounding region. So we explore this, what can be causing this in the paper a little bit more. But just to mention this briefly, we explored possibilities of, we mentioned that it may be due to volatiles within micro cold traps. It could be adsorbed water. It could be composition, such as a northite, or it could be simply a systematic effect. So the next thing we do, equipped with this spectra for all of these regions, is we try to model the spectra. So we utilize the hemispheric albedo formulation by Hackey. I'm showing the equation there on the left, in case you're interested. If not, really the important thing here are the plots on the right. So the top panel is showing the spectra for high regolith porosity. The lower panel is for low regolith porosity. And what we do is we start with 0% water, meaning we're looking 100% at dry regolith. And that is that gray curve that I'm showing there. And then we increment the amount of water that's present in our model here. So we increment for these purposes by 1%. So these are the blue curves that I'm showing between 1% H2O and 5% H2O. Now at each one of these H2O abundance steps, we calculate the off-band to on-band ratio for the model. We compare it with the off-band to on-band ratio that I was showing previously from our observations. And we use this in order to constrain how much water ice may be within these permanently shadowed regions. And so by doing so, we find that there may be as much as 1.4% water ice by mass if we assume high regolith porosity, or 1.9 H2O by mass if we assume low regolith porosity. Now that increasing albedo in the surrounding non-cold trap regions I said maybe due to the presence of water. So if this is true, if this effect is due to the presence of water, we find that this increase in off-band albedo is consistent with up to 0.2 H2O by mass. Now, taking a step back and looking at other volatiles that may be contributing to this off to on-band ratio, we start to look at NH3, SO2, and CO2. And we look at these specifically because they were the most abundant volatiles that were detected by during the L-cross mission. So there are a few loss mechanisms that could be occurring within these PSRs. They include Lyman alpha photodissorption, impact gardening, and also sublimation loss. And sublimation loss is really what's going to drive the lifetime. So for that reason, we're showing here sublimation loss rates on the left for each one of our volatiles. So we're showing H2O in black, SO2 in red, and H3 in green, and then the last one is CO2. So for each one of these volatiles, we also define a stability temperature. So this is the temperature at which 1 kilogram per meter squared of ice would survive for 1 billion years. So for H2O, we find that this is 101 Kelvin. For SO2, it is 72 Kelvin. For 63, we find 63 Kelvin. And then for CO2, we find 52 Kelvin. So then having quantified the thermodynamic stability of these volatiles, the next question is which one or which ones of these volatiles are sensitive to this off to on-band ratio method that we are using. So to answer this question, we have to look at the spectra for each one of these volatiles. So to do so, we go to the spectra from Wagner et al. In 1987, and we're showing the reproduction of the spectra on the right here. So focusing first on H2O, this is this blue curve, sort of as a proof of concept here. We look at the reflectance in the off band and the reflectance in the on band, ignoring everything that's shaded in gray. And we can see that the reflectance is higher in the off band, meaning that this would lead to high off band to on band ratios. We can say the same thing for CO2. They have a very similar spectral shape. And then if we look at the bottom panel, NH3 would also lead to a high off-band to on-band ratio, but SO2 does not. And since SO2 does not, is not consistent with this high off-band to on-band ratio, that means that by using this method, we're not going to be picking up on any SO2. So for that reason, we do not consider SO2 moving forward in our study, and we focus more on CO2 and NH3, as well as H2O. So we then look at the albedo within each one of our wavebands with temperature, since we said temperature is really driving that lifetime for these volatiles. And we see this increasing trend between albedo and temperature. So these are the red trend lines that I'm showing here. And this was interesting because we don't really know how to explain this increasing trend, but what we can say is that this increasing trend is probably not due to the presence of condensed H2O, CO2, or NH3, because as we showed with those stability, or as we showed with the sublimation loss curves, these volatiles are not stable over long periods of time at these temperatures. So something else must be causing this increasing trend, which is great for us because that means that we can normalize by this increasing trend. And that allows us to reduce these normalized off-band to on-band ratios with the annual maximum temperature that I'm showing here on the right-hand side. And so looking at this plot, what we see is a break in trend at approximately 115 Kelvin. And what I mean by this is that the ratios less than 115 Kelvin are about 20% higher than the ratios at temperatures greater than 115 Kelvin. And if we go back to our sublimation rate curves here, we see that 115 Kelvin is where water ice would be stable for 1 million years. So what we think we're seeing here at temperatures less than 150 Kelvin, we think we see the presence of water ice. And then once we start to warm up to these warmer temperatures above 115 Kelvin, we think we're seeing the sublimation of water ice, causing that decrease in off-to-on band ratio. Sorry, going back here. But one thing that, so this is shown to be consistent with water ice here at 115, but we can't really say much about the colder temperatures here at 60 or 70 Kelvin. So we don't know if the off to on band ratios at these extremely low cold temperatures are due to the presence of water ice or due to the presence of CO2 or NH3 or all of the above. So to try to decipher this a little bit more, we define a normalized albedo ratio or NAR. And that's what I'm showing here on the right, specifically for water ice. So what this normalized albedo ratio is the off to on band ratio at temperatures where water ice is stable to the off to on band ratio at temperatures where water ice is not stable. So for water, this is the ratio between 70 and 115 Kelvin divided by the ratio at temperatures greater than 150. And then on the right-hand side, we've normalized the average South Pole cold trap. So what this allows us to do is it's sort of a quick reference to look at the relative abundance. So looking at this plot, we see that Faustini, Shoemaker, and Hayworth all have an NAR value that's quite similar to that of the average South Pole cold trap, meaning that these regions may have about equal amounts of water ice as the average cold trap. Cabeus and the unnamed region, however, have a lower NAR value, meaning that they may be somewhat depleted in water, at least on the surface. And then Amundsen is somewhat elevated. So we do this the same thing for the regions where NH3 is stable. And we make a note that the regions where NH3 is stable also includes regions where water ice is stable. So assuming that this trend is due to the presence of NH3, we would then say that Cabeus and the unnamed region may be somewhat depleted in NH3, and Amundsen again is somewhat elevated. So then lastly, we do this for the regions where CO2 is stable. And then we see a different trend popping out here. So in this case, Hayworth and Cabeus and Amundsen all have a somewhat elevated NAR value, but Shoemaker and the unnamed region are somewhat depleted. So to summarize what we've talked about so far, we find increased off to on band ratios within cold traps. This is shown to be consistent with up to 1.4% water ice by mass if we assume the high porosity case. And this is generally consistent with previous studies by Gladstone et al. And also Hain et al. We also find elevated off to on band ratios at temperatures less than 115 Kelvin. This is consistent with water ice with a lifetime of 1 million years. We also find, we also investigate the NAR values for H2O, CO2, and NH3 within our 6 regions of interest. And then we also see lower albedos within the cold traps, which is consistent with increased regolith porosity within these regions. So then, as we mentioned earlier, there are many mechanisms that can bring volatiles to the lunar South Pole. And one of them we mentioned was cometary and asteroid impact. So a recent study by Mont et al. Just in 2022 actually found that for the case study of Cabeus using the data from LCROSS, they were able to find that the volatiles within Cabeus were most likely of cometary origin, as opposed to outgassing, for example, or volcanism. So in this next step, we're going to also look at a case study here. We're going to look at one very specific comet, and this is Comet Siding Spring. And in 2014, in September, LRO actually took a break from its normal studies, and it slewed away from the moon. And it did so in order to observe comet sighting spring. So at this point in time, the comet was at its closest approach to the moon. It was at 0.9 AU approximately. And LAMP was able to observe it in an anti-sunward direction during 2 blank stare observations of approximately 1,500 seconds each. So as the comets are coming closer and closer into the inner solar system, some of the ices are going to start to sublimate away. One of these ices may be H2O. That H2O is then going to photodissociate into something like a hydrogen atom and OH, which will further photodissociate into oxygen and hydrogen. And so this is a little bit of foreshadowing as to what we might expect to see in this comet. So on the right-hand side here, I'm showing the actual LAMP observations. And so LAMP is an imaging spectrograph, which means that we're able to look at both spatial information as well as spectral information. So we have the spatial information on the y-axis. So these are the physical detector rows on the instrument. And we have the wavelength on the x-axis. And we see 3 very prominent features. These are oxygen at 1304. We see hydrogen Lyman alpha at 1216. And then within the Lyman alpha, we also see a darkening of the line center. So this is due to a loss of sensitivity in the detector at that wavelength. And then we also see on the far left, the Lyman alpha ghost. So without getting into too much detail here, the Lyman alpha ghost is essentially due to the internal reflections of the hydrogen light. So it is due to these internal reflections, it is spatially inverted, meaning that while the cometary observations are concentrated within rows 11 through 14, we get additional hydrogen information in rows 14 through 17 from this Lyman alpha ghost. So as before, we're able to look at the spectra for the comet in both the cometary rows as well as the rows containing the Lyman alpha ghost. So we're showing the comet rows on the left, the ghost rows on the right. So in the top panel, we have our raw observations in black. The gray is the background and the red is the background subtracted or the residual counts. And then looking at panel A here or panel C, what we see is that oxygen is quite obvious, whereas the Lyman alpha is not as obvious. It's a little bit more fuzzy. And then looking at the right panels, the Lyman alpha ghost again is a possible detection, and I'm choosing my words carefully here. I keep saying possible Lyman alpha because we're going to get into that a little bit more in the upcoming slides. But first, sticking with the spectra here, the next thing we do is we're able to zoom into the detectability limits of the instrument. And so this is the same spectra as the previous slide. We're just zoomed in quite a bit. And so we do this in order to investigate other possible species. So we're looking at candidate species of oxygen, carbon, sulfur, noble gases, as well as CO. So the important one here is a CO fourth positive band system that we're able to place an upper limit on. So for all of these, we're placing 3 sigma upper limits on the abundance. And we find that the upper limits for sulfur, for example, are very constraining, but also for the noble gases, our upper limits are actually not all that constraining. So going back to our Lyman alpha issue here. So now I'm showing the spatial information. So this is, we'll talk about first the top panel here, oxygen. We have essentially the rows on the x-axis here, the spatial information. So 1 pixel in this case is equal to 7 times 10 to the 5th kilometers, meaning that for oxygen, for example, our observation is spanning 4 spatial pixels, meaning that the radius of the oxygen coma would then map to about 1.4 times 10 to the 6th kilometers. Looking at the Lyman alpha in the bottom panel, looking at the same 4 rows, we do not see any obvious hydrogen features. So this is where we would expect the cometary hydrogen to be. And we don't see any obvious features above the background, meaning that we do not positively or confidently detect hydrogen within our comet. So what we do then is we do what we did with the candidate species, and we place 3 sigma upper limits on the hydrogen. So now taking our oxygen observation, our hydrogen upper limits, and our CO upper limits, we then find the column density for each one of these species, which allows us to find the production rate. And so for CO, we find the CO production rate, and this is sort of the end of the line. This is where we stop for CO. But for oxygen and hydrogen, they're daughter and granddaughter species of H2O and OH. So what we do is we use branching ratios, empirical relations, and a 3-generation Hauser-like model to find a production rate for both OH and H2O. We compare these production rates with previous studies. So for H2O, starting on panel A, we find that our value is pretty consistent with the previous studies. In panel B, we look at OH. Once again, our value is within 20% of previous studies. And then for CO, this value is within 15% of previous studies. So to summarize here, we utilize the oxygen, hydrogen observations to derive H2O and OH production rates. And we also derive a CO production rate, all of which are found to be fairly consistent with previous studies. And then we place 3 sigma upper limits on a variety of different candidate species. And all of these results are summarized or explained in the publication here that I'm showing to the right. And this was published just in January of this year. So to summarize everything then that we've talked about in the last half hour, we utilize the LRO-LAMP observations of the South Pole to find evidence of up to 1.4% water ice by mass within the cold traps. We also find evidence of increased regolith porosity within these cold traps. We also find elevated normalized off-band to on-band ratios at temperatures less than 115, pointing to there being water ice with a lifetime of 1 million years. And we compare relative possible abundances for NH3, CO2, and H2O within our 6 regions of interest. And then for the cometary investigations here, we find OH and H2O production rates as well as CO production rates that are consistent with previous studies. So I went through that quite fast. So if anyone has any questions, now is the time.
Awesome. Thanks, Lizeth. That was great. Excellent presentation. So so what questions do we have for Lizeth? And I see Carl had a couple of questions in the chat. Carl, did you want to unmute and go ahead and ask those?
Sure. First, excellent talk, really nice data. And Liz, while you were talking, I went ahead and looked at your dissertation. Looks like a very nice dissertation as well. So congratulations. So your dissertation answered the second question. I think your detection is compelling. I'd just like to see all the data plotted, not just what's in the PSRs, really see what's hidden. And you didn't hide anything, just easier to see. But how about photometry? That's something that's always bothered me potentially with a 2-band ratio, and that whether, I don't know if this is true, the illumination source may be constant, that the slopes will be changing, and a 2-band is basically color, and color can change with photometry, with instant and emission angle. So could you comment on potentially that, or is there a way you can look for correlation between slopes and band ratios? I suppose since you don't see this effect outside the PSRs, you don't have to worry about it being dominant inside the PSRs. But in this case, the source for the PSRs is different than outside the PSRs, right? Where you have using sunlight, whereas inside PSR using, I'm just thinking off the top of my head, galactic and whatever starlight, right? I was wondering if photometry could be an effect. I haven't really thought about it, so I'm just looking to see what you have to say on that.
Yeah, I haven't really thought about it either.
Okay, yeah.
I guess we're sort of looking at 6 years worth of data here, or 7 years. So we're looking at a variety of different emission and incident angles. So when we average them together, I assume we wouldn't really see those effects popping out.
Right, makes sense.
Yeah.
Yeah,
That's
and someone commented this is all night side data anyway, which I didn't catch.
Yeah.
Okay.
right. Yeah. Yeah. Well, that was me thinking out loud there.
If I can add there, been working on LAMP for a long time, decade and a half probably, right? But it's only in the last 5 years where I feel like I've really understood what the albedo is that we're measuring on the night side. And it really is just that single scattering parameter, because we have a hemispheric illumination and a hemispheric emission. And Hapke has a chapter in his book all about this kind of hemispheric illumination, and it really does just reduce to the W single scattering parameter. The B and the C parameters don't really come in just with our night side technique in the first place. And so we really are comparing that W on and the W off in a very complementary way in the work that Lizeth has here across all the wavelengths. The day side maps that we have, the stuff that I showed at LPSC, especially highlighting Ben Byron's work, focuses on our day side data analysis. And there we have a paper by Liu et al. Where we've figured out some constraints on WMB. Laura Mayorga's coming back to revise those. We took a good first shot, but these things are always hard, and she's going to do one step better on that. But we have these nailed down to some degree, and certainly taking the ratios hides multitudes of sins, but as long as we don't overdo it with these wavelength things in the day side data, we're not too far off. Yeah, I worry about that too. It keeps me up at night, Carl. So thanks.
And thank you, Kurt, for clarifying that.
Yeah, that's not easy, no doubt about it.
All right, what other questions do folks have? So Lizeth, Wayne Pryor asks in the chat, I guess you saw that. If you could put the figure back up on Wagner 1987. So Wayne, did you have a question on that one, or was that just a request to
Yeah,
go back to that figure?
I may talk to her offline about that one.
Cool. And we have a couple more questions. All right, so Margaret Landis asks, how much temperature variation is there within the PSR borders used in this work? Does this correspond to some of the on-band, off-band albedo maps?
I guess I don't really understand this question. If you can explain it a little bit better, Margaret.
Right. So I see Margaret's chat only. So Margaret, I'm gonna try and dissect your question, but if I get it wrong, please feel free to comment. So I guess the first part of the question is so within your regions of interest, how much does the temperature vary? Like, are all of the PSRs are all of those regions of interest at similar temperatures, or
Okay. Yeah, so I'll attempt to answer here. So the minimum and maximum temperature for the cold traps are somewhat the same. Cabeus is the coldest, but the distribution of temperatures within those regions are different. I see that Margaret was asking about the PSR borders. So we defined for the PSRs a border of 110 Kelvin. I did a little bit of playing around with this. Does the spectra change if we mess with this 110 border? And the answer was not really. So there wasn't much sensitivity of the spectra to the PSR border, cold trap border that we defined here. And does this correspond to some of the on to off band albedo maps?
Right. So Elizabeth, I think this was related to you had those nice maps which show and I think right. So Kurt says regarding Margaret's question, Lizeth, slides 19 and 20 address as well.
And I pulled up 19 and 20 here.
Right. So these are
Right. Yes. So the cold traps were defined essentially based off of this temperature, not like Kurt is saying, not necessarily the PSRs. So we saw this break in trend here at 115, and that sort of helped define some of the borders.
Cool. And I think the second part of Margaret's question. So Lizeth, you have those nice maps where you have the PSRs, and then within the PSRs there are like colors representing the on-band off-band ratio. I think you might have had one in right. So I think, and Margaret, correct me if I'm wrong, but I think what Margaret might be asking in the second part of her question is whether those color variations you see within the PSRs, do those sort of map to temperature differences between the PSRs? Like, do we see different values of the on-band off-band of the off-band on-band ratio because they're at different temperatures, or is there maybe something else going on there?
Yeah, so I guess for statistics reasons, we really just look at the average off to on-band ratio within these regions of interest. And then when we're looking at temperature, we're really looking at every region that's at that temperature, again, for statistics regions. So we're not, for example, I wouldn't look at just the off-band within a certain small region for statistics. So yeah, I can't speak to that too much because yeah, the statistics wouldn't be too high to do that.
Cool. And we have another question in the chat from Brad Blair, who asks, have you generated any ammonia related maps?
No, so for ammonia, carbon dioxide, we're really trying to identify those based on temperature, so based on the stability temperature. So the best we could do there would be to make a map of the regions that are at or below the stability temperature of NH3.
Cool.
Then, yeah, one thing I was going to mention, as somewhat slipped my mind here, this first part of the talk that was more so concentrated on water ice at the lunar South Pole was just submitted to JGR Planets this morning. So keep an eye out for that one.
Quick follow-up on Brad's question. I think you've shown this to me before, Lizeth, but did every place that was cold enough for ammonia have a positive detection in your method?
I haven't looked at it in that sense, Michael.
Okay, well then maybe this is a suggestion for future work. Overlay those two and see if every spot that's, what is it, like 63 Kelvin or colder does have a high off-band on-band ratio. I feel like it, well, I don't want to speculate if I'm remembering the wrong thing.
Yeah, yeah, one thing to point out there would be that any region where NH3 is stable would also be a region where H2O is stable.
Right, but what bothers me about all of the different LRO and other data sets is that everywhere that water is stable does not have a water detection, or not everywhere that water is stable has a water detection. So I wonder if the same is true for potentially ammonia or CO2.
Okay, yeah, that might be something we can look at for the second paper that I'll be publishing on this topic.
Cool.
Thank you.
And I see John Gruner also has a question in chat. And folks, for questions, feel free to keep putting them in the chat, but also if you prefer to ask your question out loud, just go ahead and raise your hand using the Zoom raise hand feature, and we can call on you that way as well. But John's question is, for your albedo maps chart in figure D, can you relate the off-band, on-band colors to weight percent water?
Yeah, so since it's off to on-band ratio, as we showed with the modeling here, for the modeling, we find the off to on-band ratio for different water abundances and compare it that way to constrain the abundance of water ice. So for all of the PSRs, we found an H2O abundance of 1.4. I don't have a quick chart that I can point to and say this specific value or this specific off to on-band value is equal to this to this water abundance. So I can't say to that detail, but the average of all of the regions of interest had a water ice abundance consistent of 1.4% by weight, and then the average of all the non-cold trap regions were consistent with up to 0.2% water ice by weight.
All right, and we have another question from Mike Barker, who says, great work. So Mike has a few questions, so let's take them one at a time. How do the HAPKey modeling results depend on the ice grain size?
So the ice grain size, I believe I found it was not too, the off to on-band ratio did not really vary with the water ice grain size. And then for the regolith grain size, however, it did vary. So I talk about that a little bit more in the paper. We ended up going with 51 micrometers for the regolith grain size because that was the average of the particles within the Apollo sample that we were working with here. I also, in the paper, I talk about how it changes exactly with different grain sizes that were assumed in other studies, if that answers that question.
And the second part of Mike's question was, how does your map of positive ice detections compare to the maps from M-Cubed and LOLA? And if there are any differences, can you speculate on the reason for any differences?
Yeah, I haven't compared pixel by pixel, which pixels in our maps light up. I haven't compared those to which pixels light up with LOLA or M-Cubed. I know Schweitzer had a paper in 2018, I believe, where they sort of did that. They looked at the M-Cubed pixels and compared them with LAMP and LOLA. And they found, I believe, like 93% comparison or so. So I would assume it would be, something like that. Although I haven't, like I said, haven't actually gone through and compared pixel by pixel what the consistency is.
Talking to Paul Hain about this and Schweitzer and myself, we're all sort of putting our instruments to the edge of their detectability ranges. And so to sort of read into any one pixel, here's where the water is, kind of we're not there yet exactly. And that comparison is a good thing to have if all of them do sort of show that there's a correspondence. That's great. It's also not outside of like the statistical coincidence kind of area either. So even that would be sort of a stretch too far to some degree.
Yeah, for that reason, I was sort of comparing, the average water abundance that we get here or the average off to on-band ratio that we get from our study with the averages from previous studies, rather than a pixel by pixel comparison, like we were just talking about.
I guess I have a quick question. So the reflectance spectra for the different molecules, are those dependent at all on temperature, or does it kind of not matter?
I wouldn't think so. Michael, maybe you can say a little bit more here. I think,
What I
yeah.
will say is that I'm pretty sure we're funded to investigate that through a different project.
Awesome. So that means that was a good question. And all right, so Brad has another question. And I think this is a good question. So for anyone that attended the ClockSat workshop, so for folks who haven't heard of that, so ClockSat, I forget what clock stands for, but it's something about a continuous lunar orbital presence. So for anyone that attended the ClockSat workshop, are there any planned or possible missions that would collect far UV data that could augment the LRO-LAMP dataset? If so, how much would the resolution improve? And are there plans to image the North Pole? So Lizeth and anyone else who wants to chime in on that, please do.
Yeah, I did not attend this workshop, but I thought Lunar Flashlight was also going to be taking UV observations of the moon. Correct me someone if I'm wrong.
Yeah, does anyone know what the wavelength for Lunar Flashlight is? I realized that I think I'd assumed it was something like 3 microns, but maybe
if Flashlight is looking at UV, that changed in the last couple of years. They were going to be near infrared primarily, but that, like I said, they may have changed in the last couple of years. Paul Hain or Barb Cohen should be able to answer that.
I feel like a 325 nanometer LED or something on it, but that's not our far UV bandpass that's diagnostic of this. So I've spoken about this topic at a league sort of a lunchtime workshop a while ago, contributed to Tim Glotch's white paper and another sort of mission concept that we proposed to M5 but didn't get selected, called Selma. And yeah, we have ambitions to fly a better UV imager or a better UV spectrograph. And just in terms of different resolutions, for example, the Europa UVS instrument we just delivered to JPL has about 10 times better spatial resolution than LAMP does. So we're really excited about what we're going to do with our new generation of detectors that are in our UV spectrographs. And our instrument scientist, Mike Davis, has a nice paper about some imaging concepts that would totally improve the sensitivity and spatial resolution at the same time. So we're looking at these things, and just had a nice conversation with Josh Cahill and Carl Hibbets about some laser ideas. And yeah, Carl, I'll forward you this email on that conversation to follow up there. So yeah, we're thinking about it for sure. And I sort of signed myself up to contribute a white paper to this SAT effort, but man, I've been so busy. I don't know if I missed the deadline even. So yeah.
Yeah, actually, that's a good reminder, Kurt. So for in case folks forgot about it after LPSC, but so the ClockSat team is, so the deadline for nominating members is closed, but the deadline for white papers is, I believe, the end of the month. And so for folks who are subscribed to the Lunar L, you should have an email from Ben Greenhagen in your inboxes from a few weeks ago. And so they are accepting short white papers on what should be measured from orbit, why it should be measured, and how it should be measured. So yeah, good reminder, and encourage everyone to submit to that. And then Lizeth, could you, or Kurt, could one of you comment on the other part of Brad's question, which was about imaging the North Pole? Does the LAMP data, is the LAMP data enough to do similar stuff at the North Pole, or not quite there?
Yeah, so we have observations of the North Pole with LAMP, just as we do with the South Pole. We haven't done too much with it since the papers by Gladstone et al. Or Hayne et al. And that's, I believe, primarily due to that we have better signal to noise at the South Pole as opposed to the North Pole, simply because we have more far UV sources, illumination sources.
Interesting. Yeah, I guess I hadn't appreciated that fully before, that the illumination sources are different.
Yeah, if
All
you've
right.
ever on a mountaintop in the southern hemisphere and looked up, looks a lot brighter overall, more stars, and the spiral arm, especially that has the UV stars that are our illumination source, are like 7 times more prevalent than the North Pole. So our data on the South Pole is just much better.
Interesting. We have time for maybe one last super quick question, if anyone has one. All right, if not, we are coming to the top of the hour any minute now. So thanks again, Lizeth, for a great presentation, and we'll definitely keep an eye out for that JGR paper. And I see you have your email address on there in case anyone wants to follow up with more questions. But yeah, thank you, Lizeth, and thanks everyone for dialing in. And we will meet again about a month from now.
And thank you, Parvati, for inviting me to talk about my dissertation work today.
Sure. All right, take care, everyone. Bye-bye.